Greetings, my engineering science students. I am doing a video presentation of this PowerPoint for you all, just in case you have missed my voice, or if you prefer to have the PowerPoint read to you rather than going through it on your own. Most of the material in this PowerPoint is review of information that you've been taught since since elementary school, but you may not have thought about it in this particular light, and you may have forgotten some of the things in here. So we're going to go through and sort of review the basics of materials. Now, the reason why materials are such a critical part of engineering science is you can't build stuff without materials, and depending on what you want something to do will determine what type of material you use. For example, until we developed high quality steel, there was only so tall we could build buildings. And once they developed steel, they were able to do the skyscrapers that we now see every day and take for granted. Now, this PowerPoint's a little out of date. There are currently 135,000 unique materials on MatWeb, with new materials being developed every single day. Well, maybe not every day, but being developed with great frequency. Okay, a lot of our history has actually been defined by our ability to select and modify materials. One of the reasons why China's civilization is considered older than a lot of the Western civilization was their ability to start using ceramics. Some of the cultures that have been considered more primitive over the years were because they didn't advance from using certain types of materials into others. If you think about it, we define history by the Stone Age, the Bronze Age, etc. And then these are some things that we may be seeing in the discussion questions to think about. So basically, materials continue to change the world. For the longest time, people thought silicone was just simply sand on the beach. Maybe you use it for making glass. But in the late 50s, 60s, they started figuring out how to make semiconductors, which allows for all of the smart technology that we have today. So materials are constantly changing and advancing on there, and there's a lovely little iterative loop back and forth of everything necessary to make advances happen. Alright, so the first bare bones type of material is an element. An element is something that only consists of one particle or atom. Actually, it's one type of atom. It cannot be broken down to any subparts. And once you start breaking it down, you're breaking down atoms into protons, electrons, neutrons, and you're no longer dealing with a material. So criteria for elements, basically how we classify the elements, that's your good friend, the periodic table that you hopefully learned about in chemistry. And it's organized based on individual properties and grouped according to shared properties. The amount of how much you have doesn't really make a difference. So there are three basic ways that we classify elements. Back that up. We break elements into three categories, and they're based on two things: your physical properties and your chemical properties. Your physical properties are sort of describing how it looks. Your chemical properties are how it reacts. The three main categories, and I'm sorry my video is covering one of them, would be your metals, your non-metals, and then this little one right here are your metalloids. So you can see metal is sort of a core thing that we're arranging it from, but metals, non-metals, and metalloids. So, metals. Good things about metals, or things that make a metal a metal, is it conducts heat, electricity, either one. It conducts. Basically, the electrons are all loosey-goosey in metals, easy to move around, and it makes it easy to conduct and move things. They're hard, they're shiny, they're easy to bend, and if you look at their electron structure, they have 1 to 3 valence electrons. Next, we have our non-metal elements. These tend to be gas at room temperature, and the solids tend to be dull, brittle, powdery. They are not good conductors. They're very poor conductors of heat electricity. In other words, they are often referred to as insulators. Metalloids have properties of both. So nonmetals tend to have 5 to 8 valence electrons. Metals tend to have 1 to 3 valence electrons. Metalloids have 4. In other words, depending on the circumstances, they can behave like a metal or they can behave like a non-metal. This tends to be your silicone, your germanium. These are the things that are now being used so heavily to allow us to design circuitry on the atomic level, which allows for our super small electronics. Next main category after elements are compounds. A compound is basically a substance that has combined one or more elements. They're created chemically. So when I say combined, it's actual chemical bond at the chemical level. There. The properties tend to be different than the elements that it was used to create it from. So it's like a cooking at the atomic level. Element combinations are not random, but you have to have specific ratios. In other words, H2O gives you water, but OH gives you something completely different. You cannot break it down through any sort of physical process. You have to actually have a chemical reaction to change a compound back to its elements. A mixture is when we combine different substances together, but it does not require a chemical process to break it back down. Elements within it retain their original identities, and it doesn't have a definite ratio. You can separate them out physically as well. So, our materials tend to get broken into a couple of categories, 5 to be exact: metallic, ceramic, organic, polymetric, and composite. And so the next couple of slides are going to go talking about what's the difference between all of those 5 categories. First type is metallic. Key thing about metallic is it uses pure metal elements. These are not back that up. So the first thing is like a pure metal, and this is not done very often. Most of the time what we use are alloys. Alloys are engineered metals where we have mixed some things in there. They tend to be good thermal and electric conductors. They have plasticity, which means they're easy to bend and shape and mold, and they are also very strong. The next type of category, is ceramics. This is more than just your dishes. Actually, superconductors are going to fall into the category of ceramics. Basically, it consists of metal and non-metal elements. They are excellent insulators. That's why you see this picture right here. Those little things right there are used as ceramics, and they're used as insulators to keep you from electrocuting yourself on power lines. They tend to have high strength and do well at high temperatures, but they're also very brittle. In other words, you can smash them. Clay is one of the main ceramic materials. It can be used for all of these things there. Some of these are put together at super high temperatures or pressures to create really a lot of neat things. I'm not sure if you've ever gotten to see like a space shuttle tile or anything like that, but like with a space shuttle tile, you can take a blowtorch and just put the blowtorch on it, remove it for 5 minutes, take the blowtorch away and touch the tile, and the tile is still cool. They are very, very good insulators. Ceramics are used a lot in electronics, more than you would think for an insulator, but what it does is it allows you to create resistors, control temperatures, and it takes a lot of energy to get them hot, so when they get hot, they stay hot. Next category is our organic materials. This is where you lose me. Not a big fan of the organic stuff. Basically, something that's organic is something that was once living, or it tends to have a carbon and hydrogen in its makeup. Um, with organic materials, you can genetically alter it. It has genetics to it. Um, it's renewable. You can make more, and it's sustainable. Next, we have our polymetrics. These are mainly made of organic materials, but they tend to, the easiest way to think about this is they're plastics. And the reason why this gets its own category is because their properties are very unique. With polymetrics, you get a chain. When you take a look at when you take a look at the molecular structure tends to be like long strands, which my drawing isn't very good with this, but it tends to be long strands, which allows it to do that flexibility and elasticity. That would be why you have your plastics and your elastometers. Alright, still going on about the polymetric. There's a lot of cool stuff in polymetric. A lot of this is where some of our cutting-edge technology is in the 20th and 21st century. One of the nicest things about plastic is it's easy to form it into whatever shape you want by applying heat and pressure or molding. This excuse me. This means that it's it's cheap and easy to make things with. There are two main categories. Those are your thermoplastics. Thermosetting. Once you set it, it doesn't get remolded. Elastometers are things that can be stretched. And then vulcanization, this is actually the oldest form of handling the polymers, and that's where you get your things like rubber in there. Alright, next we have our composite materials, and they're basically made of more than one material, thus the name composite. And they design basically. Okay, hopefully this is just picking up and letting me redo this slide because I went through it too fast. Composite materials are where a lot of the really cool stuff like the Teflon and then your super light, super strong metal-like structures are coming from. Basically, you could do things in layers, or you do things with the small particles, or you have fibers that are embedded in a matrix to have stuff built around it. And that's where we're getting, as I said, the stuff like the bulletproof vests and the sports equipment that can handle a lot of abuse and still be lightweight. So, material selection. There isn't necessarily a right or a wrong. It's just trying to balance a whole bunch of different things. So whenever you're trying to pick what material you're building with, you have to take a look at the properties of that material, and you also have to consider how much it costs. So if I'm trying to mass produce something, plastic would probably be a better thing, unless it is supposed to conduct electricity. Then I would need to pick something else. So you have to take a look at what the item is and what it's supposed to do to help pick your materials. As I said here, the things you got to consider. For example, the building materials they use around the equator are significantly different than the building materials that they use up north. In fact, you can kind of see this if you ever watch HGTV. A lot of those shows are made in Canada, and a lot of things they talk about building with or doing are actually totally different down here in Texas because we have a completely different environment. So a lot of things are based on environmental conditions and whether or not you need the material to last a long time or if it's okay if it wears. These are the properties that you tend to have to consider. You have to consider its mechanical properties, its thermal properties, its electromagnetic properties, and its chemical properties. For example, gold is actually a pretty good conductor, but it's not as good of a conductor as silver. But oftentimes when they're selling audio equipment, they will advertise using gold rather than silver connectors. The reason for that is the silver tarnishes, and even though it's a better conductor, if you put it in a place where it's exposed to air, the silver will tarnish, impeding its ability to conduct well. Whereas gold conducts almost as well as silver, but it doesn't have the tarnishing aspects of it. So you have to consider all four of these characteristics. Mechanical properties. You take a look at the strength, hardness, ductility, and stiffness. You should know what all of those words mean. Hardness is sort of like how easily it can scratch. Stiffness is how easily it bends. Ductility is basically how much you can stretch and release. And strength is how much weight it can hold. Thermal properties, we've actually already looked at these this year. It's how well can it transfer heat, and how much does it expand or contract when it's heated. Electrical, does it conduct electricity? Chemical, oxidation or reduction, in other words, does it tend to corrode easily or combust easily? Does it tend to have a toxic impact on other things? Flammability, is it going to burst into flames? Important things to consider. Okay, we are now on our last slide, and you can read over this. Hopefully most of this material in this slideshow was a review of things you had already gone over in your elementary, middle school, and high school science classes. The next thing we're going to be doing is a scavenger hunt to see how many of these materials you can find around your house. So go on to step 2 and take a look at the directions for the scavenger hunt.